to this webinar in which a lot of different researchers from the drone field are attending and presenting new results, mainly on drone technology innovation to ensure transport safety. There are 3 different European projects involved in this webinar. We have drones for safety, we have also Rapid, and we have also Labyrinth. So these 3 huge projects are bringing us a lot of new results on these topics. And we have several PhD students sharing with us today their advances. And also we will have for each of the projects short presentations by the responsibles so that we know a little bit about the project and the advances nowadays. So I will be given the word first to the first project, which is Drones for Safety. And we have Emad Samuel Malki Ebeid from University of Southern Denmark to start the presentation and introduce Rapid project. Drones for Safety project. So welcome, Emad, and you have the stage for you.
Thank you so much for the kind introduction, for the invitation. I'll share my screen and I hope you can see it from the screen. Okay. Good morning. I'm Emad Samuel. I work as an associate professor at the University of Southern Denmark. We located in Odense, which is in very close to Copenhagen and also to the German side, to Hamburg. I'm the project coordinator of Horizon 2020 Drones for Safety project, and our aim is to build drones to autonomously inspect infrastructure, especially railways and bridges, to ensure their safety. We do this to avoid a scenario in which the inspectors, the humans here, are in risk and danger of their lives, especially when they inspect a part of the bridge or using a big machine like this, or also when they do some work related to railways, to be sure that the lines are okay. And also now we see more issues with the railway side due to the climate change and the more heat waves coming. So they do this, some of the rails are bulked, so they're not in a straight line. And the same, there are many parts in the electrical side of the railways that they are getting old, aged, and then you need to be inspected as well. So our mission is to remove this situation in which the human is in risk by using advanced technologies. And that is the Drones for Safety. We aim to build autonomous, self-recharging, and collaborative drone system to make an inspection of a big part of the transport infrastructure. The project has 3 academic partners, research partners, STU, Aarhus University, and Fraunhofer, and industrial partners, Del Air, NEAT, and Deep Blue, and ERIC, and Research Center from Italy, EU Center, and Eurocontrol for regulations. Yeah, we are in the same level of the other project, so we are in the last phase of the project. So the project will end in May 2023. Yeah, so that is the overall concept. One can see here. Our aim is to use power lines to recharge the drones. The drone will gain power, fly to the nearby bridges, take pictures, send them to the cloud. They will be analyzed, finding defects, and send it to the end user. They can do the same from railways. We have a very ambitious ideas to recharge from the railway lines, and also do the same with inspecting the trains. We also discovered that many of the bridges are within short distance from power lines. So if one goes 1 kilometer far from a high voltage line, in Europe, we'll find 15% of bridges. If one goes 3 kilometers, then it becomes 70%. So it's really an approachable distance if you think about a drone flying for 20 kilometers. Yeah, and that is our idea, is to make a set of drones, a swarm. They are capable of self-recharging from overhead lines. They do autonomous inspection. They run algorithm on board using edge computing and AI algorithm to detect and doing also the inspection side by training neural network to find defects on the collected pictures. Yeah, and all of that is connected through the cloud to get the mission. So where this drone should go and what kind of data they collect and where exactly which path is good for them. So more into mission control. Yeah, and the drones for safety, we built our own hardware platform. That's because we have the mentality is more research, so we'd like to get our hands dirty, opening up open source software and hardware, fixing issues, making them better, and getting it to work. So we used from other EU projects, we use a flight controller called Pixhawk and Pix for autopilot to make the drone to fly. So one by having this system can make any piece of metal like this with motors to fly and controlled from the ground. And here we come with the companion computers. We use advanced computers called MBSoC, multiprocessor system on chip, that is FPGA based. And the processor basically has two parts. A CPU, we run ROS2, and we have an FPGA, we run heavy algorithm like a computer vision algorithm. And that way we relax the CPU by delegating the heavy task like computer vision task to the FPGA side. And this computer is connected to the sensors that they are lightweight and fitting for our mission to detect the cables and doing the inspection. So the sensor here, we use for example, magnetometers. We use also cameras, but also we use millimeter wave. We will see in the next slide how they look like. We have the communication between node to node through ROS. So we have a node is a drone, another node is another drone, and then we do the communication through Wi-Fi network, and also same with the cloud. You can read more about the hardware. We left it open source, so if one is interested, you can read the article mentioned here. You will get also slides afterwards. Yeah, and this is one of our prototypes in which we have the Ultra 96, which is an MBSoC board lying underneath. It is like the size of a Raspberry Pi, connected with a camera, and also with the millimeter wave sensor to identify the cables and to know the position of each line. We go to something called off-board mode to enable the autonomous mission, and then there is a control algorithm to control the drone to the mission that it needs to follow the line, to recharge from the line, or to go to another side or another line. So we have a lot of autonomy. So that is one of the videos showing you how the system works. So we use here in simulation. So we have data collected from the drone. So here you can see the purple dot identifying the cable. And one can select this, you can say, I would like to go flying with the drone to stay 1 meter far from this purple dot. And you can see here the drone in autonomous flight orientating itself 1 meter far from the power line. So we use that, it becomes really like user-friendly. Once I go to line phase 1, say 1 meter, half a meter, touch the line, that is from the GUI, and then we give it the command, and then the drone using these two sensors, the camera to know the orientation of the line, and the millimeter wave to know exactly where is the line. And we actually get really good results thanks to the clean background here, because we see the sky. So we have a really good and accurate system. Yeah, and that is one of the latest work in which the drone was making a mission like this here. Yeah, that is our latest article was published in IEEE Access Journal, and it is on open source, open access. So you can also see how the system and algorithm are designed and are working. Next part in the project is energy harvesting. So we used when we charge, we have two types of lines. One is AC and one is the DC. AC line, so we benefit from the magnetic field. And here we use a split core current transformer and then energy with coil to harvest energy, so work as an energy harvester. So we have to surround the line. So we grasp and then we induce current. The other interesting part is the DC lines. A DC means we need to connect between 2 points, plus and minus, and requires a very advanced circuit that we are almost to finalize. To basically, it's like DC to DC converter to lower the voltage and charge the drone. Advantage here, it is lighter, so we don't have a core, but it's also quite challenging to work with because the DC line. So we have to connect 2 points together. So now we are working on making a drone to do 2-step landing, and we are approaching the target now. Other part, when it comes to a real high voltage lines, we see the drone has to touch high voltage wires. So we shield our drones. You can see here they look like a bit a copper color. That is because it's a Faraday cage. So here we touched 150 kilovolt, and that was okay, the Faraday cage. And then we touched 400 kilovolt. That is basically in the street. You can see the houses behind, and that is was not okay. That's because there was some issues and the Faraday cage. So we have to redesign the protection side. And then here we start, we understood what went wrong, and then we have a better drone that is quite stable under a high magnetic field, and you can see there were some sparks here. So we put the harvester, and then we went with the drone to the street again, and then we closed on the line to recharge the drone. And in that case, the drone is simulating a scenario in which it is recharging from an AC line by grasping, closing the harvester, and recharge. We had this work 5 months ago, and was the first time in the world that a drone system can do that, to charge from a street power line. Moving towards drone swarm, so here the drone is basically designed also to communicate with another drone, and build a better or a faster inspection mission using Wi-Fi, but also with 4G and the LoRa network. And that is a test of these 2 drones. They are on a mission to follow lines. One chose to follow this line, the other one follow the other line. They communicate together to coordinate, to understand where to go. And here is a mock-up of a bridge in which also the drone is following the bridge autonomously. They are not really following these markers, but it is using vision to follow the bridging. This is about mission control, and Lea will speak about it later to show you how the system is designed, so I'll skip it. And here is the AI for fault detection. And here is the AI part, is basically to collect as much data as possible, label them, and saying that is a broken maybe wire, or there is a crack on the bridge, and so on. And in the project, we are using a supervised machine learning algorithm. We tried also with unsupervised, but the results is not that great. So the future idea will be here, the end user will see a 3D model of the bridge, as you can see here. That is from our partner Altea. And then based on the detected images, the images will be stitched on the bridge. So the owner of the bridge can zoom in and find the defects. And there is a video showing how this works. So yeah. So after the drone are flying and taking pictures, they are sent to the cloud. the cloud has a 3D model of the bridge. The AI algorithm is running on the collected pictures. And then here the AI identify some cracks, and then from the data one can know where exactly this crack is. And that is the mentality here of the AI algorithm. Yeah, and that's it from my side. If you are curious, you can also read more about our publications from dronesforsafety.eu/outcomes. Or also, if you have any question, you can write me an email or also see our group website from DIII/SDU.dk.
Okay, thank you very much, Emad. Of course, we will have time to ask questions around the end of each group's presentations, right? So around 9:30, we will have time for questions for all the participants of each project. So now we have Lea, right? Lea Matleković from University of Southern Denmark, and the presentation will be about multi-UAV path planning for continuous linear infrastructure inspection. You have around 5 minutes, Lea, okay? So now this is your turn.
Thank you very much.
You're very welcome.
Let me open the presentation. Okay. Are you able to see my in the presentation mode or just the presentation?
Yes. Maybe you have to put it in the presentation mode.
Yeah, it is, but I have a lot of screens. Let me try again.
Okay.
Okay, now it should be good.
Thank you.
Okay, good morning, everyone. My name is Lea, and today I decided to present you my ongoing research work, which is continuous path planning for inspection of linear infrastructure like railways or power lines. And actually, these algorithms are part of Drones for Safety project. And the work of my team in Drones for Safety is to develop application for global high-level path planning. So whatever we can calculate in advance before the drone starts inspecting, we try to do it on the cloud and then send information or send waypoints to the drones to fly. So in this problem, the question is, if we have a number of drones, here you can see the orange dots, which represent drones, how should we divide this graph? Let's say that these blue circles represent power lines in this case, but it could be railways or any kind of like graphs looking like this. So the question is how to divide this graph so that when now we should divide it in three different parts because we have 3 drones for inspection. How to divide it in order to achieve the minimal time for the inspection and to cover all of the infrastructure. So basically the goal is to have an algorithm which we could calculate once and then continuously just let the drones inspect the all network. Let's say we should select like all this island and then let the algorithm work for itself. So first we started with describing the problem. And first, we describe the problem as a graph covering problem. And so we define the nodes, and then we defined edges. And each edge, we gave it a cost, which in our case represents the distance between two nodes. And then we have a number of drones, which is k, and the objective is to find the decomposition of this graph into k different graphs. But in this case, when we have just inspection distance, when we divide the graph and create two graphs, some solvers we found could usually find this solution. So basically, it divides the graph into one part, which is like nodes 1, 2, 3, and the cost is 16, and then the other part where the cost is 24. And then first drone should start inspecting the first graph, and then the second drone will inspect the second graph. And the total cost of inspection is then 24. After a little bit of thinking, we realized that if we just allow drones to pass through from one node to another without inspecting, and if we assume that inspection flight time will be longer because the drone will probably fly slower in order to capture everything with camera. And if we just want the drone to fly through from point to point, it can fly in higher speed. So we decided to redefine this problem and define the graph weights with weight for inspection and weight for just flying. Basically, weight for just flying will be less than weight for inspection, because inspection will require slower flight and it will cost more then. So in that case, we developed a simple constraint solver, which was able to solve this problem. And it divided the graphs in these two graphs, where the first graph is also cost 16 for inspection, and it also continued inspecting this edge between 3 and 4. But the other drone now did the inspection of the first 3 nodes, but then it just flew through this part in order to reach node 4 and to inspect this edge here. So in total, the cost for the first drone increased, and now it's not 16, it's 20. But the total inspection cost is lower than in the first case, and this is what we wanted to achieve. So in this case, it's 22. Now, we encountered a lot of issues, and we would also like to work more on this problem, because we still need to consider starting points and ending points. This could make the problem more complex, because it will probably decrease the optimality of the solving. And also, we would like to include charging part where the drones actually figure out that they need to charge, they hook on the power lines, and then that should also be included in the cost. And the issue we are dealing with right now is that for larger graphs, it takes a lot of time to calculate it with this simple constraint solver we developed. So we are trying to work on some more heuristic solutions in order to find maybe not that optimal, but quicker results. And that would be it. Thank you for your attention.
Thank you very much, Lea. Very interesting topic. Okay, now we have Viet Duong Hoang from University of Southern Denmark, and the presentation will be about magnetic energy harvesting for charging drones from overhead power lines. So please, Viet, you have the screen for you.
Yeah, thank you. I hope you can see my screen now.
Yes, yes.
Great. Hi, everyone. My name is Viet. I am a PhD student.
Sorry, Viet, can you use the presentation mode? Because we are just, we can see your slides, but not in presentation mode.
Okay, I'm trying again. Okay, I have to share my entire screen. Can you see it in the presentation mode? Yeah.
It's okay. Thank you.
Yeah. Okay. Hello, everyone. My name is Viet from University of Southern Denmark, and I am a PhD student. And today I will present to you my PhD thesis called the magnetic energy harvesting for charging drones from overhead power lines. And energy harvesting is a process in which energy is derived from external sources, processed and stored in an internal storage unit. They can be solar power, thermal energy, wind energy, and so on. And in Drone for Safety, we use the energy from the power line cable, as you can see in the left figure here. And the drone will fly close to the power line and grabs on the power line and recharge its battery from the magnetic field around the cable, because we already have the 60 or 50 hertz AC current flowing into the power line. And as you can see in the top right figure here, IP is primary current, and we already have the HR is magnetic intensity. And in order to harvest the energy from the power line current, we use a magnetic core. And this magnetic core have the copper coil wrapping around, and I1 is the power line, and I2 and V2 is the secondary current and secondary voltage. And the output of the coil will connect to the charging circuit after that, and the battery will be charged from this coil. And the theory behind this circuit is Ampere law and Faraday law. So the most important part of this is the magnetic core. So we need to analyze every characteristic of magnetic core to choose the best magnetic core to use for the energy harvesting. So the first one is permeability. That is a parameter that indicates how well a magnetic material can conduct flux. And we figure out that permeability, the use of magnetic core with high permeability is not always necessary, because you can see with the permeability around 2000, if we keep increasing it to 10,000, we don't have much more harvested power. Or in other words, it becomes saturated. And the second characteristic is flux density. And the ideal core should have the highest saturation flux density. And we figure out that the carbon iron had the highest magnetic flux saturation. Ferrite is a common material for current transformer, but it has very low magnetic saturation, so that is not a good choice. What about number of turns of the couple coil? We figure out that the higher number of turns, the higher load voltage, as you can see in this graph. But the number of turns does not affect the maximum harvested power. As you can see, number of turn of 200 or number of turn of 1000, the harvested power stay the same. And what about the core shape? We figure out that the magnetic core with a long core with a small diameter is much better than selecting a short core with a large diameter. As you can see in this is a short core with a large diameter. It has the harvested power but 152 watt. But for the long core and the small diameter, harvested power is over 200 watt. So that is the very interesting thing that we figured out. So that is the end of my presentation, and thank you for your attention. And if you have any question about my thesis work, you can send me an email. This is my email, and thank you very much.
Thank you very much, Viet, for your presentation. Also very challenging, I can see. Okay, now we have the turn for questions and answers. So you are very welcome to ask anything you would like to ask. Anybody? You simply you only have to open your microphone and ask. I have one question for Lea. I would like to know the software, Lea, you use for this segmentation. How did you plan the problem using which software?
So you mean the constraint solver?
Yeah.
So the constraint solver is developed in a software called MiniSync.
Oh.
I didn't know about that before, but it's an open source project from some university in Australia.
Okay.
And yeah, it's just like a programming language for solving constraints, and then you define constraints, and you already have inside implemented solvers. You choose which solver, and then it solves your problem with iterations. That's why it does not work for large graphs.
Yeah, I know. Would you be so kind so as to share the link with us through the chat? Okay, great. Thanks a lot. Very interesting. Okay, and Viet, for you, I have a question, because of course you are concentrated on the system, the charging system, right? But since this is connected directly to the drone, right, and you have to approach the power line, and this is a very, very difficult, right, operation.
Yes.
How is that system connected to the drone? With a rigid element, or have you thought of something softer so that there is more compliance when doing the connection? Have you worked on that part, or maybe not?
I mainly just work on the charging circuit. I select the right magnetic core, choose the best, and design the charging circuit to make it to help it to harvest the energy from the power line. I'm just working on that.
Okay.
Also, at the moment, I also work on the magnetic gripper, because as you can see, the magnetic core has a square shape, or it can be a circular shape, and it includes two parts. And when we clip around the power line, the magnetic field around the magnetic core can be used to attract two parts, attract each other, and the magnetic core can act as now a magnetic magnet. So when we fly close to the drone, and two parts of the magnetic core will attract each other, and the drone can be hang on the power line by the magnetic field of the magnetic core. Yeah.
Very interesting. Very, very challenging.
Yes.
Yeah. Good luck, because there are problems, more soft problems and then hard problems, right? So this is a very hard problem.
Yes. My work is very strongly related to the hard way.
Yeah.
Instead of the soft way. Yeah.
Yes.
Yeah.
Okay. Very, very, very nice. Thank you both guys, and also of course thank you, Emad, for your presentation. We have finished, but please let me know if there are more questions for them.
Yes, maybe I have more. One more question for.
Of course.
For Lea.
Mm-hmm.
So, if, for example, two drones are to fly through same part of the graph, as you said, one for inspecting and one just flies through this part of the graph, how do you coordinate those flights? So maybe they fly together, or maybe one flies first and then the other one? So they don't collide, maybe? I don't know. How do you coordinate that?
So I don't coordinate it, but
okay.
I rely on people who will be developing local onboard algorithms. So let them implement like collision avoidance. So if they maybe collide, they should just like avoid each other and continue. That's how I solve my problem.
Okay, thank you.
Then you can call Blanca. You can then call Blanca to solve this problem. Nice, very nice. Okay, Fernando, you were asking something, or anybody else? No.
Yeah, one question also for Lea.
Okay, great.
What are large problems for you? So how many nodes and how many edges?
So I don't know exactly, but if you remember the first image I showed you, that graph we couldn't solve because it was just impossibly big. So maybe it's, I don't know, 500 nodes. This is just the like from the feeling. But so we solved some smaller graphs with, I don't know, maybe up to 50 nodes. But higher than that, it just becomes like impossible with this constraint solver.
Yeah,
and then it also depends on how the graph looks like.
Mm-hmm. Yeah, I'm using a different solver called Groby.
Mm-hmm.
Also path planning, but completely different problem setup. And I can have up to 10,000 optimization variables and 30,000 constraints, and it will be solved in 2 seconds.
Oh, can you tell me like what is the name of this software again?
Yeah, I can post a link in the chat.
Yes, please.
It's also free for academic users, and else it's pretty expensive.
Yeah, okay, that would be great. That's why I love these seminars.
Okay.
Thank you very much.
Thank you very much. Very, very nice questions and very nice sharing activities here. Thanks a lot. Okay, no more questions, I think, right? Okay, then we have time now for rapid project. We have James Riordan from University of the West of Scotland to present the project and give us an overview of the advances. And of course, now, James, this is your stage. You can start whenever you want.
Yeah. Hi, so I'm James Riordan. I'm presenting as coordinator of the RAPID project. So the acronym is Risk Aware Port Inspection Drones. So I'll just toggle forward. So we're a consortium of 9 partners. We're a fairly even mix of industrial partners and academic partners. The project is led by EWS, but it's embedded in the Port of Hamburg by our partner, Hamburg Port Authority. Hamburg port is quite an interesting use case. It's the third largest container port in Europe. It's quite an inland port. It's about 40 kilometers in the River Elbe, and it covers about 75 square kilometers of docks and quay walls and piers and so on. It sits within the city of Hamburg, which is quite interconnected by a series of waterways. So one of the approaches we take in Rapid to be able to access the sites that we want to survey is we're working on integrating a swarm of drones with an uncrewed surface vessel. So the one that you see in the image here, which is an offshore survey vessel that's manufactured by one of our partners, X-Ocean. So the key focus of the project, we're split across a number of use cases involving emissions monitoring, ship hull inspection, coastal zone emergency response. But the main priority, I think similar to other projects in the cluster, is monitoring the condition of the transport system infrastructure. So we're speaking here about bridges and the lock network throughout the port. So across this site of 74 square kilometers, we're typically looking for features of interest that are sub-millimeter. So looking for things like hairline cracks to discover cracks that we didn't previously know about, or to discover if there's any changes to cracks that we did know about. If there's any changing morphology, might indicate some deeper structural deficiencies. So to come from the start of the project, which is about 2.5 years ago now, up to a final demo in about 4 to 6 months' time, we engaged a TRL escalation strategy where most of the partners will have access to local test sites, in particular operating out of airfields. So this has given us quite a degree of experience in engaging and operating with air traffic control, local police services, city regulators, involving maritime regulations as well, because we're quite a maritime focused project in terms of the use case in a port and harbour. And also experience in operating in field with crewed light aircraft and helicopters and the challenges there, and specific operational risk assessments and so on. So we, UWS, operate out of Straven Airfield. Our partners, University of Limerick, they operate out of Newcastle Aerodrome on the east coast of Ireland, and this was where we had one of our first consortium tests back at month 22, so April of this year. It's quite fortuitous that airfield is beside the sea, so it's a coastal airfield, and a rail line runs through it, so it has provided opportunities as well along the way to build up expertise in survey inspection of, for example, railway bridges and so on. Within the Port of Hamburg, as well as the showcase bridges, we're also quite focused on inspection survey of more routine infrastructure like the lock network. So the Harburger lock shown here has become one of our test sites. We had a test in Hamburg in September where we brought the whole consortium together to test the swarm and the various building blocks within the service. Typically, our workflow, we will deploy multiple drones in a swarm configuration, spatially segmented, and allocated tasks according to their payload sensors. So what we will typically do as a first stage is we'll do a high-level LiDAR survey to get the wide-scale and global view of the site, identify any hazards, and from there we'll get some very high-resolution 3D photogrammetry models of the site, and this starts to build out a digital twin that we use for mission planning, but also then for containerizing the data that we collect. And the end line of the service then is an embedded neural network which resides on board the drones, processes the camera imagery as it's collected in real time to detect any cracks in the imagery. The approach that we've taken is we've used a commercial off-the-shelf system, the DJI M300s, and we've adapted them with either standard or custom sensor payloads, depending on whether the drone is being modified for a survey task or whether it's being modified for airspace surveillance. And we embed or we mount our own embedded compute, which are typically either AGX or NX systems from NVIDIA, and running our own custom software. So within the consortium, I think there's about 7 M300 drones that are all configured for a specific purpose. So for example, in the image here, the yellow drone would be collecting either LiDAR or photogrammetry imagery, while the red drone is flying actually quite low and close proximity to the wall, collecting photographic imagery for the crack detection. To get ground sample densities of sub 1 millimeter, we need to fly within 3-4 meter proximity to the wall. So what we will typically do is we'll have another drone performing a sentry role that's able to monitor and observe the other drones in the swarm and monitor for incursions as well, just making sure that we're keeping to separation distances. One of the things we've done here is obviously to provide remote mission support and energy management and transport around the port site. We've integrated with an uncrewed surface vessel. This has required a whole series of stages around autonomous landing and takeoff from the USV. Our energy management solution is that when the drone lands on the USV, it is grabbed, put into a fixed hold, and the batteries are hot swapped. So there's a mechanical hot swap system. We will typically, with a 2.7 kilo payload, we'll get about 35 minutes of flight time. It would typically take about 35 minutes to charge the batteries, which have a 550 watt energy budget. Using this system, we get a hot swap in under 3 minutes. So it significantly improves the duty cycle of the drones when you would be in a situation where you wouldn't have a human present to manually swap out the drones, or swap out the batteries, I should say. This is all fed into an energy digital twin as well, which optimizes the solar harvesting on the USV and compensates for the fact that some of the panels are now removed to provide the landing gantry for the USVs. All in, when we bring all of this together, the fast AI selection of cracks in the imagery, the swarm multipliers, and the improvement in the duty cycle with the hot swap, we're typically looking at somewhere between 10 and 30 of an efficient 10 and 30-fold of an efficiency gain in terms of being able to speed up the missions. So in terms of improving the productivity of the overall service, we've been actually quite happy with the results we've seen so far. The other aspect of this is, because we're introducing drones into a densely populated environment where there can also be other drones and light aircraft present, one of the things we very much focused on is the hazard perception side. So we will operate within this specific operational risk assessment that's produced by EASA, where we need to identify hazards pre-mission, strategically and tactically mitigate for them, but also consider the overall liability of the operations. And moving more towards performance-based standards from the current risk-based standards, we've started to focus on things like the pilot to drone, drone to drone, drone to swarm, and incursion detection. So we've a number of firsts here that we're due to publish. First of all, we have one of the first point-based detection and localization systems embedded on a drone. This is using LiDAR and radar to detect drones within a swarm and incursions on a perimeter out to useful ranges of 100 meters plus. Our partners, University of Limerick, have also developed a system for detecting incursions by light aircraft and helicopters that has performed out to about 3 kilometers, which far exceeds the requirements for beyond visual line of sight monitoring. And we've also started to investigate the pilot perception challenges, where we may be operating in environmentally challenging conditions, like if it's heavy rain or into the glare of sunshine, to ensure that while we automate all our missions, if a ship or a helicopter or an uninvolved person enters the situation, the pilot has to take physical and cognitive control of the drone and move it to a containment area if we're operating at the extremities of visual line of sight, this can be particularly challenging. So it does allow us to rehearse these kind of high-risk strategies in a digital twin, as well as evaluating the performance of the perception AI before we deploy in the field, and it becomes part of our risk assessment process. So that is a very quick overview of the RAPID project and where we're currently at in terms of progress. We have a final demo that we anticipate will be scheduled for May of next year in the Port of Hamburg. And yeah, we'll circulate information on that once we have a date nailed down. So if you want any further information, please just contact myself or Suhansu or any of the PhD speakers who will follow this talk. Thank you.
Thank you very much, James. Very, very amazing research. Congratulations. So now we have the turn for Alexander Dove from the same university, University of the West of Scotland, with the presentation and MLOPs approach to deploy trustworthy AI for drone detection and localization. So please, Alexander, the stage is yours.
Good morning. Can you see the presentation? Is that all okay?
Yes, perfectly well. Thank you.
Fantastic. Hello, everyone. My name is Alex Dow. I'm a second-year PhD student at the University of the West of Scotland. Thank you, James, for the overview of the project. And today, yes, I'll be looking at an MLOps approach to deploy trustworthy AI for drone-to-drone detection and localization. So the project's work is based in the EU's regulatory framework for specific operation risk assessment, SORA. From its basis in safety, we aim to prevent accidents such as two drones colliding into each other. And that's what my work specifically looks at. So the method looks at the embedded system. So why is there a need for a customized embedded system? Well, the off-the-shelf systems within the area we're working aren't designed for a real-time workflow. So we had to work within very strict and on the limit size, weight, and power restrictions that we designed an onboard compute using the NVIDIA Jetson AGX and made use of a LiDAR, the Livox Avia, a Wi-Fi antenna to provide connection to the ground, a top-mounted casing, which included all of the OSDK connections and the power connections and the onboard compute itself. We then use MLOps as a framework to design, develop, and deploy our artificial intelligence network in real-world scenarios. So here you can see the work that we were doing in Hamburg. In figure 4, you can see a swarm mission being conducted. James touched on the roles of each of the different UAS in the swarm. And you can see that we're using a real world and digital twin combination here to validate the work that we're doing. In figure 5, you can see what the LiDAR sees. A drone detection and localization situation provided by the network that Dr. Manduhu has devised for aerial work based off the ground-based LiDAR known as point pillars. And then you can see the MLOps side of things over in figure 6. You can see just one of the many different things we analyze and use to flow back into the training and select the right data, the data that we're missing, the areas that the network is weak in, to then retrain the network and increase its performance through active training. Moving forwards, we have further testing coming up in May 2023. I will be working to optimize the neural network's performance using those previously mentioned MLOps training cycles. For that, we'll be using the data collection drone that you can see in the top in figure 8. And in figure 9, you can see our setup for the live real-time situations. The Livox Avia is actually the same LiDAR unit used in the DJI L1 that you can see in figure 8, but the DJI L1 isn't able to give us the real-time information, hence the need to set up our own and engineer our own onboard embedded situation. But yes, nice little picture as well in the bottom left of the team who were fortunate enough to go out to Hamburg and do the training that we were doing, testing, sorry, that we were doing in month 28 of the project. If you do have any questions, feel free to ask some later on in the webinar today, or you can email me on my contact email address there. Thank you very much.
Thank you very much, Alex. Very nice research. Okay, now we have the following presenter, which is who is Hector Arroyo-Gonzalez, University of the West of Scotland, with his presentation about intelligent drone perception using airborne radar. So, Hector, the stage is yours. We cannot hear you, Hector.
Yeah.
Okay, now we can. Okay, thank you.
Thank you. Yeah, thank you for the presentation, Concha. Yeah, so my name is Hector, and I'm also second-year PhD student at UWS. And today I'll be talking about the use of radar to improve drones perception. So just a bit of a project recap. The project started in February 2021, so a year and a half into it now. And it's actually a collaboration between 3 entities, which is UWS, the Data Lab, which is a funding body here in Scotland for data and AI projects, and Codeplay, which has come in as an industrial partner. The main objectives of the project are twofold. So on one hand is to deliver a radar-based algorithm for the detection of other aerial vehicles with a main focus in drones. And the second objective is to use this algorithm as a use case for Codeplay's SQL open standard. And what is SQL? So basically most of AI these days is done through NVIDIA cards that rely on CUDA as the backend for operations. Now what SQL allows us is to take all these algorithms and port them to an other party software hardware service such as AMD or Intel cards. Key to drones, it also gives us more control over key parameters such as performance, heat generation, or energy consumption, which are quite important for drone operations. So the idea is to have the final demo running on this software. A little bit of the background of the project. One of the challenges that we faced at the beginning is that there's not really an off-the-shelf radar solution for drones. DJI, the drone manufacturer, did release an option, but it's quite a short range, only sort of like 30 meters, and is mainly used for poor weather conditions and like obstacle avoidance. So we turned into the automotive sector, which is well advanced in this field, and we went for this system that is like sort of like a smartphone size, so to speak. It gives us the range up to 400 meters depending on the target characteristics, and most importantly it has the right weight, size, and power suitable to be mounted on the drone. So with this setup, basically we've focused on ground-to-air and air-to-air work. The ground-to-air work, it's been mainly to understand the sensing capabilities of the radar. So for this, we've set up pre-planned missions and specific data collection strategies that we've then used to develop 2 different AI pipelines. So the first AI pipeline is projection-based type of network. So it takes the 3D point cloud and projects it either onto the horizontal or the vertical plane. And the features of each point of each radar return are passed as channels to that image. The network returns a per pixel label. And as you can see here, it does quite a good job at discretizing between the ground returns that it gets here and the drone returns that it gets up in the air. The second network, the second pipeline that we've developed is a point net, just to establish a comparison between the two. And this network does ingest a point cloud as it is, and it returns as a per point label. This network is a better suit for this type of data because of its use of 3D point clouds, but it's also potentially slower. So that's again where SQL comes in handy to take control over all these parameters and try to come up with the most efficient and optimized solution for real-time detections. And now we move on to the airborne implementation. A lot of this work bringing the radar up in the air. It's thanks as well to the work that my colleague Alex just mentioned, and also help from other partners within the Rapid project. And it's basically just getting everything together and making sure that it's a robust system that can take off and can monitor the space as we want. We have a really nice field setup. This is an airfield to the south of Glasgow that we use for our experiments. We typically do so by monitoring an area of a volume of air. Basically, in this case, is this volume that is limited by these 8 points, which runs parallel to this runway here. And the typical scenario is the drone with the radar could take off here and hover around this point here, and then we'd have a second drone doing incursions into this airspace, and we could be able to see how the radar senses and detects that. And that's sort of what I'm trying to show in this visualization here. That's the drone hovering here, and that's a second drone now entering the airspace, and eventually around 120 meters this time, it picks up the incurring drone. And the work now basically is to develop these scenarios, to increase the complexity of them, maybe adding new agents to this, and just wrap this with all the metrics with the publication. So yeah, that's about it. Any questions, please feel free to get in touch.
Thanks a lot, Hector. Very nice presentation. Also very challenging the project. So good luck. Okay, now we have the following presenter, who is Ben Bartlett from University of Limerick, who is speaking about automated high-resolution inspection. Okay, please. Yes, hi.
Can we see there now?
Yeah, perfect.
Perfect. Hi, my name is Ben Bartlett. I'm a PhD researcher with Chris. My supervisor is Jarduli. So I'll be talking about automated high-resolution inspection workflow for unknown structures. One of the Rapid project deliverables is a 3D reconstruction for the purpose of analysis, both in augmented reality and for crack detection. The port is a challenging and dynamic environment with many overhanging structures and large vessels moving through the port at any time. With manual detection methods, it is near impossible to survey due to the static nature of the process. The standard procedure currently for a mapping mission is to create a 2D plan over an area, and a waypoint mission is automatically generated based on the payload and desired overlap of the images. To generate a 3D mission, including height variations, this currently requires a lot of user input and knowledge of the area. There are a few current methods to generate missions. One such method is UGCS, which is possible to generate these 3D missions, but these are just often vertical variations of the horizontal 2D mapping missions. So the overall workflow, I'll summarize here. The mission is, as usual, is created to cover the general area. In addition, the operator decides on an area of interest for the high resolution scan within this general area. The first level scan is completed over the area. These images are then downloaded and a low resolution 3D model is generated in combination with a new flight mission for a close quarter inspection. This flight plan is reviewed and then executed. This process is repeated as many times as necessary. Usually this is completed in 2 stages. So the initial mission plan begins the same as any other mission. You choose your approximate area that you wish to survey, generating a mapping mission on the controller at the height and with the required payload. Here we can see a lock in Hamburg as the area we wish to survey, for example. The next stage is to designate the following areas. The home point is where the mission will start and stop. The target area of interest is also defined. There's also the option to specifically exclude an area denoted as shown here. If this area overlaps with the interesting area, this area will not be reconstructed. Another example I will focus on during this presentation is a bridge inspection we completed in Wicklow. Here you can see the high-level survey plan and each photo that will be captured. So the user starts the mission as they would and waits for it to be completed. Once this mission is complete, the drone will land at the home point as designated. This flight can then be completed fully autonomously. Now we're looking at the full workflow. So this download process is not currently fully autonomous, but it's currently under development. So we have developed an Android application which utilizes the onboard MSDK, mobile SDK. This runs on the controller, requiring no additional hardware. Once the drone lands, the images from the survey are autonomously downloaded from the drone to the controller. So currently this is just a button click within the MSDK application, but we're going to be using flags in relation to the mission status to determine if the drone has successfully completed the stage 1 survey. Model and mission generation. We have a bottom side PC being utilized for stage 2 reconstruction. A web server has also been installed on the controller to allow for the processing PC to access these payload images. A script is running on this PC, which waits until all images are downloaded once the survey has been completed. This works for any size survey of any area. The only current limitations are the download or computational speeds. This script then creates a Metashape project, generating a depth map, a 3D model, a DEM, and finally a waypoint mission for the high resolution inspection. The parameters for this are decided upon based on the infrastructure in the area. For example, the bottom of the lock is lower than the home point, so this has to be accounted for when the parameters are selected if we want the drone to fly into the lock. The GSD achieved with these models is about 15 millimeters. So it's quite a low resolution model. So once the mission is reviewed, we can automatically fly the mission that was generated. As you can see in these videos here, the drone is flying very close to the infrastructure and taking multiple images at different angles, heights, and orientations to be able to generate a much higher resolution and extensive 3D model of this area. This would be impossible to generate manually. These images also run through another process to determine if the cracks are in the infrastructure exist. So the GSD achieved with this model is then a 0.7 millimeter GSD. And then if higher GSD is required, another mission can be repeated as the same process goes on. If any cracks are detected as well in that separate process while this 3D model is being generated, another close quarter inspection can be completed on those areas of interest and a high resolution mosaic image generated. That's the mission. That's it there.
Thank you very much, Ben. Also very interesting presentation. Okay, now the turn is for Matheus Cardoso Santos from University of Limerick with the presentation Automated Landing System for M300 Drone to ASV. So please, Matheus, start whenever you want. Thank you.
Can you hear me?
Yes,
yeah.
Perfect.
Hi everyone, my name is Matheus Santos. I'm a PhD student at the University of Limerick under the RAPID project, and my supervisors are Dr. Jarduli and Dr. Petar Tislic. So in this presentation, I'm going to give you an overview of the progress we've made during my PhD, and the title of the presentation is Automated Landing System for M300 Drone to an ASV. So the market of drones is a huge market at the moment, and it was valued at 13 million in 2020, with many applications in entertainment, agriculture, defense, and also infrastructure. So the automation of this task has been targeted by researchers in the last years and should become a reality soon. However, when we are moving from UAV pilots in the field who has a line of sight to beyond vision line of sight systems, has a significant risk associated with it. And the problem is that one of the most risks is the landing phase, and it's during the land phase when you have uncertainty on the landing site that you have a high risk of a collision. And when we are dealing with ASV is even higher risk because you can just miss it and fall in the water. That's why the system we are proposing at the moment, we have our drone here, and our landing pad has a marker on the landing pad and a GPS device that is sharing the GPS location. So when we start the landing procedure, the drone receives the GPS location and fly to that position, and then we change from the GPS position to the visual-based landing. And at the moment, we have this cylindrical area where the drone is detecting the marker, and we have these different heights when we have a different radius tolerance. So up to 40 meters, we have a radius tolerance of 1 meter. And as this drone is descending, we are just straightening this tolerance. So 50 centimeters. When we reach the mark of 5 meters, it's 30 centimeters. And at the last 2 meters, it's 10 centimeters. And then we can land the drone. So the workflow of the systems, we start from the DJI node, and then we ask for a position estimation. If we don't have, we check for the GPS position. If we don't have, we request to the platform, get the GPS position, again, request the Aruco to have the position. If no, get the GPS position, send that to the aircraft, and then go to the position. Again, start the DJI node. When we start detecting the marker, so we just switch for our PID controller, and then we start our landing. Our system is composed by the M300 drone, and on top of it, the NVIDIA Jetson NX as the onboard computer that's responsible for receiving the data and do all the processing and send the commands to the drone. As a payload, we're using the Zenmut H20T that has the zoom feature that allows us to start the landing up to 50 meters. And we're integrating the system with the ROS system. So a demonstration of our landing is placed on the port of Hamburg, and is a fully autonomous landing. We have our ASV here, and you can see now for the last 2 meters, the last cylinder is activated, and then we have like a 10 centimeters precision. So the drone takes a little bit more time just to ensure that precision, and then land right on the ASV, because otherwise, if you miss it, you just fall in the water. So this ASV has a hot swap battery system. So as long as we finish the landing, the hot swap, we just activate, and then we're going to change the batteries for the drone, and we are ready to go for the mission again. So just completed the landing, and then you can see that the hot swap system is starting. It's coming, you get the drone back, and then you swap the batteries. So just to summarize the presentation, we presented the landing system integrated with the ASV. It's suitable for offshore operations, so you can do your inspections or any other mission that you might just come back to your ASV, just change the batteries and keep going. So it's a solution for a fully autonomous system. You have the long range landing with the zoom feature, so we can go up to 50 meters, detect the marker and start the landing, and the integration with the hot swap system. That's it for me. Thank you for your attention.
Thank you very much, Matheus. Very, very interesting. Okay, now we have the turn for questions and answers, so you're very welcome to ask. Freely open your microphones and please ask. Anybody?
Hi, I hope you guys can hear me.
Yes.
Okay, my name is Durlabh Maharishi. I am joining all of you from India.
Okay, nice.
And I'm sorry, my camera is not working today, so would not be able to show my face. But first of all, just extraordinary presentations. So thank you to each one of you. I think it's really wonderful the kind of work that all of you are doing. My question is more or less collective. It's not really pinpointed to any one of the presentations. Is that when it comes to the development of all of this drone tech, how open are you for international alliances for this project? Or is it, as of now, I understand it is funded by the EU. So is it limited in terms of collaboration within the EU, or are you open to ideas and discussions from outside?
Maybe great. Yes.
I can feel that one. So each of these projects will typically have an impact and exploitation strategy, because the key objective here is to migrate the outputs into professional practice, depending on the stage that they're developed to. So this particular project, it's a TRL5 output. So while the technologies will be demonstrated in a real world environment, it'll be a controlled environment. There will be another round of research and development to replicate and scale them into a commercial service. So within the consortium, the beneficiaries are typically European and associated countries. But in terms of partnership development then, as the IPR develops, yeah, I think you'll find that nearly all projects that are funded by the Commission are very open to internationalization of the outputs.
Okay, that answers my question. Thank you so much.
Thank you, James, for your answer. Yes, this is totally right what you said. More questions? I have one for Hector. If you could be a little, just a very short description about the implementation. I'm interested in how you implement because you showed a slide focusing on the implementation of the radar and so on, right? Could you describe a little bit more in detail the different parts in the implementation?
Yeah, so the system is not far from what Alex described. So there is an onboard drone that is attached with a bracket that goes into the DJI gimbal. Then that radar feeds the stream of radar data into an NVIDIA NX module, so the same as Matheus was showing. And there's this onboard computer does all the processing in the drone, basically. So that's the preparation for the real-time inference.
Okay. Now this is clear. Okay, so everything is done on board.
Yes.
Okay, nice. Thanks for the clarification. More questions, guys?
If I may, I would just want one more question. This is from India and a little bit more precise and more technical. I just wanted to understand in terms of anti-collision, when these drones are operated, what exactly is the tech or the method that is being used? Because I understand when I say anti-collision, it's more like if it's an amateur who's at the pilot seat, who's piloting the drone, and there is a possibility of collision with the with the surroundings for the lack of good piloting. How are we avoiding that exactly?
I can probably take this one. So the reason that we're developing these embedded detection algorithms is to work alongside the GPS location systems that are already on the drone, as well as the drone's detection capabilities, kind of short range obstacle avoidance. Now, these aren't always perfect, hence why we need to have these new technologies being developed. But in terms of the sensors and the systems that we're using, as listed before, it's a mixed suite of LiDAR, radar, thermal, and regular visual cameras.
Okay, thank you very much. Okay, then now we have to shift now to the next and final project, which is Labyrinth. This is coordinated by Luis Moreno, who is not able to be here today, but I will be introducing the project and the different objectives. So Blanca, please, could you share the presentation for me? Thank you. Can
you see it?
Yeah, perfect. Thank you.
Okay.
Thank you very much. So this is Labyrinth. So in the next slide, you can see the different partners and objectives of the project. The main one is to create and validate new drone swarms applications to enhance safety, security, and efficiency in the civil transport system, right? And we do this through the research and development of 4D path planning algorithms. This is for implementation in the ground control stations, but also we develop EU space services to support the drone swarms auto guidance, right? So there are 13 partners from 5 different countries here involved, from different countries, as I said, Spain, Germany, Austria, Belgium, and Italy. And of course, you can check the complete information using the link you have available in the slide. So the objectives of the project, is in a very brief way, is to, in a controlled environment, to eliminate the need of drone pilots in order to control swarms. Swarms of up to 10 drones through a new auto-piloted technology. This is the purpose, and we use different scenarios to demonstrate the technology and the algorithms we are developing. So we have to validate the drone swarm pilot services in a seaport scenario, as you can see in the slide, but also we use the same technology and demonstrated in for traffic transport surveillance operations. Also, another demonstrator is in the airport scenario, and a very challenging one is the emergency assistant operations in urban areas, because we want to shorten the time for reaching the casualty and help in case of need, right? So, but in parallel to all these activities, we also put an effort on achieving progress in accelerating the European Union's regulatory adaptation and public acceptance of these technologies, which, as you know, is quite challenging too. And also, we analyze and propose new business models related to this diversification of Labyrinth to other sectors and applications, very much in the line that James commented before. Okay, so what we do is very simple as a concept or as a scheme. We have the 4 different user cases and related to transport, the ports, the roads, the emergencies, and the airports. And this is treated from 3 main parts or technologies. One of them, the green one that you can see surrounded by a circle, is the path planning and path control problem. Also, to face that, we need, of course, 5G communications, and of course, cybersecurity. So these 3 main objectives are treated in the project, and we are showing today some of the advances in each of them. And of course, we do this, yeah, sorry, Blanca. And of course, we do this, the previous one, please. Yes, thank you. We do this taking into account standardization and certification aspects, of course. It is implicit in the different developments that we do, also regulatory aspects, and of course, with the supervision of the project managements coming from income. Okay, now we can go to the different scenarios we are analyzing, and we are testing the different approaches on. First of all, we have the road transport pilot. DGT, the Spanish public body for road safety policy, is involved, and we have the road with the cars and different elements in the road, and we want the drones to be responsible for different tasks. In general terms, we want a speed control, we want a vehicle distance measurement, plate identification and vehicle tracking, and also traffic counting and traffic monitoring in general terms, right? So this is one of the scenarios. The other scenario is the waterborne transport pilot. We have vessel inspections there, seaport infrastructure monitoring and surveillance, and also threatening operation monitoring. So these are the main things we are supporting here with the help of the Italian Seaport Authority. Okay. Next one, we have the air transport pilot. In the airport, we have the drones for different functions like bird scaling, pavement infrastructure inspections, as you can see, also airport surveillance, and to avoid unauthorized access, like for instance, a external drone or people or whatever. And then the last one, which is the emergency pilot. Here we have surveillance operations like identification of casualties, escape routes, points of medical assistance, potential risks in the area, and so on. And then we have an important issue here is the communication with the medical assistance services and the coordination of the transport to the casualties. So this is SAMUR and XSpace, are the two main partners responsible for these two last pilots. Okay, so next slide, just to finish. The general assumption we considered when starting the project are the following. We have the UAVs with an autopilot and basic automatic takeoff and landing capabilities. The UAVs has a direct RF link with the ground control station, and the task or mission assignment is decided by an operator. So this is the starting point. We want to improve this, and then the objectives are the following: the coordinated, the conflicted path planning. This is one of the important things we are presenting today for the swarm of UAVs operating in the local area, executing different basic piloting missions. Also the path control of the swarm, and the continuous and safe communications between the UAVs, the ground station, and so on, based on 5G, satellite, and Wi-Fi, depending on the availability. Today also we are presenting the advances on this topic, and of course cybersecurity of the whole system. So this is my presentation, and now this is the turn. We are shifting turns here. First of all, the presenter will be Fernando Quevedo from University Charles III in Madrid, and he is presenting a path planning network service design and architecture. Okay,
Blanca, I can present myself, so don't worry. I just corrected that, and so I hope you can see my screen.
Yes.
Perfect. So, hi everybody. My name is Fernando Quevedo Vallejo. I'm part of the Labyrinth project at the university. Well, I'm a PhD student at Carlos III. I'm part of the Labyrinth project. I was tasked with the path planning network and how to create it. So before continuing, one has to take a look at how the current flight scheme for drones are made. So nowadays it's highly regulated. You can only fly in normally some exact zones, not in every zones. And also it's very unorganized, in the meaning that there's no cooperation between drones and there's no coordination. So the aim of the Labyrinth is to create a unified flying space so any drone can fly freely and coordinated with every drone, guaranteeing safety and other sites. No, so in order to create or service or path planning services, one has to look at the inspiration from other sites. We can look at air traffic or car traffic, but soon we realized that they are not that similar to the drones, since cars are only operating in a two-dimensional space. You can even say that they are graphs because you only have the roads where you can travel. And planes also use flight levels that can be extrapolated to 2D dimensions. No, and drones can fly in a three-dimensional space. No, but also cars and drones have a very good advantage that it's a driver or a pilot that can guarantee the safety of everything. And if anything fails, it's a fail-safe operator. No, and finally the energy. Drones are very constrained with the energy, and you have to make as optimal paths as possible so you can guarantee all those. So looking at this, we can extrapolate some requirements for our service. So first will be the energy. We have to guarantee that the paths are as simple as possible, so we can make the paths as long as possible, and other things. And at the same time, we have to make a secure environment, so no drones will collide with each other or with the environment. So the use space has to be created. And finally, coordinated, because having all the other parts, but at the same time, the drones collide, conflict with each other and stop their flight because they are on the same path, can consume the energy. So it's another requirement. No? So there are many ways we could go out, but we settled down with a centralized service where there will be a path planner that every user has to use in order to create its path. No, so to the architecture, well, a first network architecture we created, it's adding a UTM that will be charged with storing all the petitions from the drones, and at the same time controlling the safety of the drones so they don't fly as close as they can, and also a planner. This planner can be embedded in the UTM, or it can be in itself a web service. No, and it will provide all the paths coordinated for the drones. No? So as I told before, the UTM will be the ingress point for a network. It will be the front end, other terms can be used, and will store all the petitions that will be sent to the planner. So the planner has all the other plans and can create a plan that it's coordinated with the others and doesn't stop in mid-flight. No? One thing to consider about the UTM, since it's the ingress point for our network, would be the protocol to communicate. No? There are many options. You can use your HTTPS, you can use WebSockets, or you can use your own proprietary protocol. We prefer to keep it as simple, so HTTPS was our first option. However, security concerns may cause us to change this thing. And at the same time, the payload, the data that we have to send also have to be in a format. There are a lot of formats. The one of simplest and most compatible with everything, it's a JSON. So in Labyrinth, as I told you, we settled down with HTTPS connections with a JSON format for our messages. No. And then we have the planner. I'm not going to discuss how to guarantee the coordination between plans. I'm more on the architecture and the design of the network. My colleague Blanca will talk later about those parts. So, but one thing to consider is planning. It's a very source intensive task. So you have to divide. We settle down with clusters. So we divide the unified space into different areas with difference. So you can have all the load balance in any area and don't overload the service. No, we use Dockers in order to create that. You can use other tools like Kubernetes and other things that will be much better. However, if you are starting, I recommend using Dockers. By this division of the planner into different into a cluster with different areas, we ensure the scalability of the project and that we can interact correctly with everything. No? So to summarize all, the final network design for drones will be that our drones will be interfacing with the UTM that will also have a database and to store all the petitions and will connect to the planner that can be embedded or can be in itself a web service. And the planner will create all the paths that will be coordinated and secure for the UTM and the drones to use. No? That's it. Thank you for your attention. If you have any questions, you can ask me later. So I pass on to you, Blanca.
Thank you very much, Fernando, for your nice presentation. Now, Blanca, this is your turn.
Yes.
You are presenting performance analysis of path planning and conflict management strategies for UAV systems.
Okay. I can hear you a bit bad. I don't know if that's my connection, I hope.
But we can hear you perfectly well.
Okay, so hey all, my name is Blanca López, and today I'd like to present some of the work of my group, the robotics lab, and myself for the Labyrinth project. This past year, we have mainly focused on making the strategies we presented last year robust and usable for the rest of the project participants. So as Concha said, one of the main goals of the Labyrinth project is to eliminate in controlled environments the need for drone pilots to control swarms of up to 10 drones through a new autopiloted technology. So in this framework, the robotics lab has the responsibility to develop the needed strategies to plan the mission trajectories and also the conflict management strategies to avoid conflicts between the vehicles when flying. So in this project, the two types of mission we are considering are go-to-point missions and coverage missions. In this presentation, I'd like to focus on some latest results obtained for the go-to-point missions. Here on the right, you can see an example of the type of environment we are working with. They have a resolution of 5 meters in every direction. And in this case, this corresponds to the Santiago Bernabeu area in Madrid. So for these go-to-point missions, we have worked with the fast marching square algorithm, which provides the characteristics listed in this slide. So to obtain a path from a starting to a goal position in the environment, this algorithm works by computing the arrival times of an expanding wavefront in an environment represented in the image on the right. And this expansion is carried out based on this viscosity or velocity matrix represented on the left image. So we can induce some desirable characteristics to the computed trajectories by modifying conveniently this viscosity matrix. For instance, we have assigned and established flight levels to ease air traffic according to flight direction. This flight level is not just a fixed altitude, but it is dependent on the ground terrain level and on potential obstacles of the environment. Another constraint we can add is blocking or fencing areas. For instance, in this image, a no passing zone marked in red has been added, and also an avoidable or risk zone marked in yellow. And also by modifying this viscosity matrix, we can achieve that the path planner is speeded up. So for instance, in this case, we limit this wave expansion with a vertical trench suitably oriented from the starting point, the red point, to the goal point, the yellow point. So another example to speed up the path planner could be this 2D projected planner developed. In this case, considering the flight is going to be performed, as I've just said, in a flight level, the obstacles interfering with this flight level are projected into a two-dimensional map, and then in the path is computed in this map, and then the height of the path is conveniently reconstructed. And for the management of conflicts, we originally developed for the UTM a speed control strategy. So first, considering that we know the position of the vehicles, we perform a safe takeoff control. And then when flying, if two vehicles are getting too close to one another, closer than a given threshold distance, we just make one of the vehicles stop and the other one continues its flight. So the criteria to assign these priorities is shown in this table, which have yielded good performance. So maybe some conflicts may not be resolved by this simple strategy. So these conflicts are detected and resolved by dodging maneuvers performed by means of free flight passages. These free flight passages consist on just modifying this viscosity matrix I was just talking about, so that no two different trajectories cross each other. So this strategy can act as a conflict management strategy on its own, just by computing free conflict trajectories, right away, or used with the speed control strategy for dodging maneuvers. So here are some results for both scenarios for after 8 hours of simulated flight. These are local simulations performed in MATLAB for the Santiago Bernabeu area. So for the speed control, here in these tables, we can see that the established safety distance of 7 cells, 35 meters, given the resolution, is maintained for every case. We can also see that the waiting times for the safe takeoff and for conflict during mission are maintained at low values. And also we can see that the computing time for the path planner and for the speed control loop are maintained at low values as well. For instance, for the longest possible path in this scenario, that is about 750 cells, the computed time for the path planner is of 0.36 seconds. And lastly, for the scenario with the free flying trajectories, we also obtain that the safety distance of 7 cells is preserved in every case. And also, as in this scenario, we don't have the safe takeoff control, more completed missions were obtained and more UAVs could fly simultaneously. And also we can see in this table that the computing time for a new mission can be obtained after about 3 seconds or less. And finally, these are some publications that cover this work for the Labyrinth project. Currently, we are working at adding the time dimension directly on the path planning level, the so-called 4D path planning. So, for instance, with the path free flying trajectories, we may cause unneeded blockages of the environment. So, adding this time dimension at the path planning level, we can ease air traffic efficiently. So that's all for my part. Thank you for your attention.
Thank you very much, Blanca. Very interesting presentation. Okay, and now we have our last presenter, who is Victor Sánchez from University Carlos III, Charles III of Madrid. And hello, and you are presenting Communication Infrastructure Manager for Fully Connected Airpass. Okay, so you are the presenter now. Thank you.
Okay, can you see my screen now?
Yes.
And in the presentation mode, right?
Yes.
Okay, perfect. So let's start with this presentation. First, my name is Victor Sánchez. I am a postdoctoral researcher at Universidad Carlos III de Madrid. And during the following minutes, I will present the research entitled Communication Manager for Hyper-Connected Remotely Pilot Aircraft System Environment, which is basically an evolution of the research article that I presented the last year in the Labyrinth webinar. So let's start with the presentation. Until today, civilian drone operation primarily include a single vehicle, but the evolution in this field and also in this research area have allowed the provisioning of more complex services that are based on multiple drones, giving rise to more complex scenarios that will need to transmit many more information streams. We'll have a considerable number of alternatives for this data transmission, and all these features inside a highly volatile and dynamic environment. And in order to control and handle these new scenarios with a lot of data to transmit and a lot of the alternatives for data transmission, we have developed a software entity known as the Communication Infrastructure Manager. This Communication Infrastructure Manager is a complete communication operator designed for drone environment. That allows the creation and establishment of network between the different actors of the system, I mean the different drones and the ground control station, as well as the automatic selection among the available communication channel among the different interfaces of the system. The architecture of this communication infrastructure manager is shown on the right part of this slide. And as the picture shows, this communication infrastructure manager relies on different technologies for its correct operation. On the first hand, it uses software-defined networking, also known as SDN. Basically, taking the advantage of SDN, we obtain a centralized and global management plane that made it possible to design and program the behavior of the drone network. On the other hand, it uses virtual networks. The virtual networks are created to complete dynamic tunnels over the 16 drone infrastructure. And in this way, the selected virtual network changes thanks to the decision made by the SDS controller. And these changes are made transparently for both the ground control station and the drone application. And finally, this communication infrastructure manager uses a network monitoring application that collects the information and the metrics from the network and from the devices. For example, the round trip time between the ground control station and the drone, the packet loss, or the available bandwidth, the jitter, the power consumption. And with all this information, this network monitoring application makes some reports to the SDN controller, and this is the input the SDN controller has in order to make the decision that affects to the network. The following slide presents the reference scenario that will be used in the Labyrinth use cases. These reference scenarios include the 3 domains presented by my colleagues in the previous presentation, that are the drone domain, the ground control station domain, and also the UTM domain. And additionally, in order to enable all the connectivity between all these domains, we include an external service domain. Okay, for example, in this case, is required for enabling the communication using the public internet. You can see a VPN server here in this external service domain. And as you can see in this image, the communication infrastructure manager that is in blue is located within the drone and the ground control station domains, since these 2 domains are the ones that may include several communication alternatives. The figure indicates that each domain will have 4 communication alternatives, but the number of interface may vary depending on the Labyrinth use case. It can be bigger or it can be less than 4. And also something significant here is that you can see that the SDN controller, that is, let's say, the brain of the network, the one in charge of making all the decision, will be located in this case in the ground control station. As we have time limitation, I'm not presenting the results of the experiment that we did in order to measure the performance of the system, but I want to highlight that this communication infrastructure manager is not only tested in a laboratory environment, but is also tested in a real flight campaign environment with the Instituto Nacional Técnico Aeroespacial, the INTA, that is a partner from the Labyrinth project. And I think this is everything. Here you can see the published papers to check the work that we did during the Labyrinth project. And now we are working currently in this article that I present today. So if you have any question or you have any interest in to know further details about our research, you can ask me or you can send me an email and we can talk.
Okay, thanks a lot, Victor. Very interesting presentations. Now we have the time for questions and answers. Anybody? Please feel free to ask. Someone wanting to ask anything? I know this project very well, the Labyrinth project, of course, but I have a question for Blanca and Fernando. How is it for you to integrate, for instance, Fernando takes the planners, right, that Blanca develops, and he has to integrate it in his system, right? How is this? Which are the main difficulties that you find when implementing in the real system, right? The planners.
Well, I believe I have to answer that more. The main concern is when embedding in the planner, you have to guarantee the stability and all those things. And many times the planners come and you haven't taken that one case that is like it's an extreme case, and that's my main problem, because I have to check constantly, and sometimes there are some things that are overlooked, and you have to find it and then talk with the other and correcting and those things. So yeah, that would be my main thing. Also, variable names, it's something that is very, very useful. We have a lot of trouble because one has an uppercase and another one didn't have, and that has wasted a lot of time, but it's not that much a problem. The other one is the main, at least my main concern would be.
Mm-hmm. But the maximum time you spent implementing some of the planners?
Well, I don't remember really. I have spent a lot. When we were starting to create the network, I wasn't very aware of how to make it, so maybe I spent a month, but I wouldn't say it's because of the planner that Blanca gave me or anything. It's more like I didn't know how to make it, and until I got to a proper point, it took a lot of time for me, and that's it.
Okay, thanks a lot, guys. Okay, more questions? Nobody else? Okay, then. So thanks, everybody. We are now closing the webinar. Thanks, first of all, to all the partners and projects responsible for presenting their projects. Really think these projects are really amazing. There are huge of research and researchers behind, and the things we do here are very, very not only challenging, but I would say that they will sooner or later change the market and the technologies involved in drones, right? So thanks a lot for your cooperation, for having the time to share your advances with us. Hopefully you learned a little bit more on what we are doing, and also maybe you become more interested in these topics if you are new in the field, right? So thanks a lot. For sure, you have the agenda, you have all the details to contact all the presenters in case you need to ask something more specific. You are very welcome to do this, and I encourage you to really brainstorm about the ideas we shared today here, because this is the important thing, brainstorming. And hopefully we will have this seminar again in 1 year. So I'm quite anxious to see the new advances, and of course you are very welcome to participate again and show the advances of your project. So thanks a lot, everybody, for coming. Take care, and see you in the following webinar. Thank you very much. I don't know, Garbiñe, thanks a lot for the amazing organization, for keeping us on track, which is quite difficult, and for making it possible. So thanks a lot, Garbiñe, and see you soon, hopefully, and please take care. Okay, see you all. Bye-bye, guys.
Bye-bye.
Thanks for coming.
Thank you very much to everyone. Bye-bye. Thank you.
Thank you, Garbiñe.